Hi everyone, my name is Sławomir Kolasiński and I will talk about the Alexandrov Theorem in Minkowski Spaces. First of all, I would like to thank the organizer for inviting me to give this talk and to make it available for wider audience. Okay, so the topic of this season is isoperimetric problems and geometric inequalities, and the Alexandrov Theorem is clearly connected with this topic. But before I state even the theorem, I have to introduce or recall several notions about GAPPF sets. So let us first fix notation. So if you have a random measure mu, you can compute the density, the n-dimensional density of a measure at x is, just to recall, the limit as r goes to 0 from positives, the measure of the ball over this, and having that, so assume mu is a measure over some r big N. Okay, having this definition, we can now define what is the essential interior of a set. So assume A is a subset of Rn plus 1, and essential interior of A is the set of those points in Rn plus 1 for those points x, for which the density, the n-dimensional density of the Lebesgue measure, and maybe n plus 1 here as well, restricted to the complement, to the complement of A at x equals 0. This is the essential interior, and now we can also define the essential boundary. Essential boundary of A is the set of those x in Rn plus 1, for which, it's the complement of the essential interior of A, sum with essential interior of the complement. Okay, and now having that, we can say when A is a GAPPF set, so A is a GAPPF set if the n-dimensional measure of the essential, here is n plus 1 here, of the essential boundary is finite. Actually, I should define it locally, so it's finite for any compact set. Now, GAPPF sets have a well-defined notion of the exterior normal vector. So we will call a vector as is in Sn is so we call U an exterior normal vector to the set A at some point of the essential boundary. Okay, let me call it B if and only if the following holds: density n plus 1 density of n plus 1 Lebesgue measure restricted to those x. I take x minus b, scalar product with U is positive. I take this half space, intersect with A, and compute the density at B. This should be 0. And a similar condition for x, scalar product U, but now without A and B. And this defines a unique vector U, which we call an exterior normal vector to A at the point B. Great. Now, to go further, we need another definition. We will work with a non-Euclidean norm. So let us take F to be a norm. We will usually assume F is C2 alpha smooth outside of the origin, but in general we only take a norm, and we can now define the perimeter. The perimeter, it will depend on this norm F, and take a set A, of GAPPF set A, and you just integrate over essential boundary F of the normal vector, and with respect to the Hausdorff measure I didn't say that here we will write NAB. This is the normal vector. U is the exterior normal vector, and for this we use this symbol NA. Okay, so the perimeter functional just integrates the length, non-Euclidean length of the normal vector, of the Euclidean, usual Euclidean normal vector, along the essential boundary of A. So in case f is the Euclidean norm, this is clearly the usual perimeter functional. So this will be simply the measure of the essential boundary of A. Now, to define the isoperimetric problem, we need to define the class of competitors for our problem. So let us call this class of sets A, calligraphic A or whatever. So this will be subsets of Rn plus 1 A, such that, well, they have finite perimeter, but not locally, not only Cacciopoli. Cacciopoli sets have locally finite perimeter. In this class of competitors, we take only sets of globally finite perimeter, and fixed volume, say, we can normalize it to be 1. So this is a class of competitors. And now we can define the isoperimetric functional. Call it I, F. This will be the ratio of the perimeter to the Lebesgue measure. Of course, we have to take, this has to scale in a proper way, so we have to raise it to some power. So this is to the power n, and this is to the power n plus 1. Okay, and now it is clear what does it mean. Okay, so minimizers of the isoperimetric functional are what you would expect. It's just isoperimetric regions, but we are mostly interested in critical points of this functional. So what do I mean by critical points? Critical points, well, first you take, so maybe I should write A is a critical point of this IF if given a one parameter family of diffeomorphisms, such that, well, H0 is just the identity, and the set of those x such that HT x is not equal x for some t in some neighborhood of 0. So this is a closure of this set. It's compact. So we are only considering those smooth one-parameter families of diffeomorphisms which start from an identity and they move points only in some fixed, in some compact set. So they are local. They don't move everything. Okay, so given such a one-parameter family of diffeomorphisms, if there holds the derivative at 0 of the perimeter of the isoperimetric functional equals 0. This is the definition of a critical point of the isoperimetric functional, and the fact is, it's not very hard to prove. The fact says that if A is a critical point of IF, if and only if there is a constant, so we call it C, such that, now I have to write, well, F normal vector of AX, and then something that I will call the mean curvature, F mean curvature of the boundary, of the essential boundary, X, scalar product with the normal vector is constant. So it does not change on the essential boundary. It's a constant. This expression is constant. Okay, I should also tell you what is the mean curvature. And the mean curvature in this context is defined in a variational manner. So is defined by differentiating, actually not the isoperimetric functional, but the perimeter functional. If you differentiate the perimeter functional, it means that you put d over d here, right, and put it under the integral, differentiate it, and then you will get some expression, and this expression is exactly what is the mean curve. Okay, so the mean curvature is defined the following way. So we let B be the essential boundary way, and then once you differentiate this expression, of course, here you push forward with some diffeomorphism, so the normal vector actually changes. You have to see how it changes, but I will not do the computation here. I will only give you what comes out of it. So if you differentiate under the integral, what comes out is the following. You integrate the trace and I have to define what is G. So G is just the vector field generated by this one-parameter family of diffeomorphisms, or to put it other way around, this one-parameter family of diffeomorphism is the flow of this vector field G. Okay. And now I have to tell you what is mu as well. So mu is just the measure, the Hausdorff measure weighted with this function. So the Hausdorff measure restricted to the essential boundary with this additional weight, f evaluated into normal value. So this is mu, and now I have to tell you what is p. Pa, well, I will not give you the definition, but I will just give you some properties. Pa is a projection, which means that if you compose it with yourself, it is still the same map. It's a map from Rn plus 1 to Rn plus 1, a linear map. And it is a projection onto the tangent space, approximate tangent space, to the measure mu at x, for mu almost all x. Great. So this usually is called the first variation, f variation of the varifold n-dimensional varifold associated to the boundary, evaluated at the vector field G. So this is, if you know varifolds, this is just the first variation of the varifold associated to the essential boundary, evaluated on the vector field G. And the mean curvature is defined so that this expression you can kind of differentiate by parts, putting the derivative onto the measure and onto p, say, and you will get rid of differentiating G, but you will end up differentiating everything else, and you will end up with some vector, some function here with vector values, scalar product with G, integrated against mu. So if this can be done, so it's not necessarily true that this equality holds, but if it holds for some function, for some vector function hf, we call this function hf the f mean curvature or mean f curvature of the boundary. And if we take a critical point of the isoperimetric functional, then any critical point of the isoperimetric functional has this property that this can be expressed. So the first variation given a priori by this formula can be expressed by another formula, namely this one, and the vector against which we integrate is called the mean curvature. So if you are wondering, in case B, this set B is a smooth or a C2, at least C2 manifold, then it has mean curvature defined classically by second derivatives and of the parameterization, say, and this notion of this variational notion of the mean curvature coincides with the classical one in case B is smooth. But in case B is not smooth, it's just a Cacciopoli set, then Cacciopoli set satisfying this identity, well, you cannot define it in a classical way, but you still have the mean curvature defined in a variational way. Okay, recall that F was a norm. To state the Alexandrov theorem, we still need a few more notions. Namely, if f is a norm, there exists something that is called the dual norm. So the dual norm, denoted by f star, is given by this formula. Okay, so this is the usual dual norm, or some people call it differential dual, or conjugate norm, or adjoint, convex conjugate, or convex adjoint. Never mind. We will call it the dual norm. And there is, of course, the ball. The f star ball, centered at A and radius r, is defined this way. Okay? And this is called the Wolf shape. The Wolf shape. Having all that, we are now ready to state the Alexandrov theorem. Well, around 1956. So, the Alexandrov theorem works for embedded, smooth, compact, connected hypersurfaces in Rn+1. In particular, what is important, they are supposed to be smooth. Because he's using PDE techniques, elliptic PDE, some maximum principle and things like that. And he's assuming constant mean curvature. By constant mean curvature, I always mean that this holds. So that in case, and Alexandrov theorem is only for Euclidean mean curvature, which means that f is just the Euclidean norm, which means that this is equal to 1, and hf is the classical mean curvature vector, and we take the normal, the normal vector, and we take the scalar product with the normal vector, and we assume this is constant. So by constant mean curvature, I mean that this is constant. Well, this. So any such smooth, compact hypersurface in Rn+1 with constant mean curvature must be an n-dimensional sphere. A more recent result by Montiel and Ross states that in a similar situation for M with the same assumptions on an embedded smooth compact connected hypersurface, but not constant mean curvature, but some other thing constant, namely we let HR to be the F-symmetric polynomial in the principal curvatures of M. This is all classical, meaning using Euclidean norms. So if you have the same M with the same assumptions, embedded smooth compact connected hypersurface in Rn+1, still smooth, then and not constant mean curvature but constant HR, then it must be a sphere. Having a smooth manifold, you can define not only classical principal curvatures but also the principal F curvatures. So in case here you have a trace of something, right, and you expect HF to be trace of some, might be not symmetric, but maybe some bilinear form, and you can actually prove that in case F is not Euclidean, something non-Euclidean, then HF is and B is smooth, like at least C2, then you can derive formula for HF, and it will actually be the trace of something bilinear form, and you can prove that this bilinear form, maybe it's not symmetric, but it has all eigenvalues real. It has exactly n real eigenvalues, and these eigenvalues will be called principal F curvatures or F principal curvatures. So there is something like the notion of principal curvature for smooth manifolds in case of non-Euclidean norms. And in 2009, He, Li, Ma, and Ge proved that M is just the boundary of some wolf shape. So the role of the sphere is now taken by the boundary of a wolf shape, which is also a sphere in some norm, in the conjugate of the dual norm to F. Now, all these results that I mentioned, Alexandrov, Monty-Ross, Heli, Mage, work with smooth objects. So a priori, they assume M is a smooth object. And quite recently, Delgadino and Maggi proved that they were able to reduce the assumptions on M. So recall that in general, our class of competitors contains all Cacciopoli sets with globally bounded, finite boundary measure. So the natural class of competitors are Cacciopoli sets, and these old results kind of always assume smoothness. But Delgadino and Maggi in 2019 were able to prove a similar result for non-smooth objects, so assuming only M is M in A. So any Cacciopoli set with finite volume and being a critical, so okay, maybe M equals boundary A in A, and so A is a critical point of the isoperimetric functional, but without F. This result is only for the Euclidean norm. So I omit this F here, and I mean that I is the Euclidean isoperimetric functional. So assume A is a critical point of the isoperimetric functional, Euclidean isoperimetric functional, and M is its boundary. Then this A must be a finite union of balls, Euclidean balls, of equal radii. So they prove this is the Alexandrov theorem with the smallest assumptions on M, a priori assumptions on M. So we only assume M is the boundary of some Cacciopoli set. And with these assumptions, they were able to prove A is a finite union of balls of equal radii. Now, this is a real... there is some real difficulty in lowering assumptions on a priori assumptions on the regularity of our hypersurface. And to understand why, I will give you the sketch of the proof of the classical proof for smooth objects, so that you will see where it is used, the regularity of the surface. Okay, so now we will consider the smooth case. Assume the boundary is smooth, and we will present the so-called Monty-Ross argument to prove the Heinze-Karcher inequality. So what is the Heinze-Karcher inequality? So we introduce this function h, which is the mean curvature vector, scalar product with the normal vector. F can now assume F is a smooth norm. So maybe here F smooth, outside the origin of F. F is smooth, B is smooth, and we will prove the Heinze-Karcher inequality. To prove the point is that the equality holds if and only if A is a wolf shape or a finite union of wolf shapes, which will actually prove our theorem. So we need to prove that any a critical point of the isoperimetric functional must satisfy this Heinze-Karcher inequality, equality, and if there is equality here instead of inequality, then we will deduce it must be a wolf shape or a finite union of wolf shapes. First, let us define what we call principal curvatures. So So the eigenvalues of this map, here you have the gradient of f composed with the normal vector. This is some kind of a vector field. You differentiate it and you get a linear map from Rn plus 1 to Rn plus 1, and you take the eigenvalues of this map now. And it turns out that the eigenvalues of this map are all real. You have exactly n non-zero, or maybe 0, I don't know. Well, you have all the eigenvalues are real numbers, and these real numbers are called principal curvatures. And we usually denote them kappa. And we order all these principal eigenvalues in non-decreasing order. So the nth one is the biggest one, and the first one is the smallest one, maybe negative. One remark: if W is a wolf shape, so just a ball, F star ball, so it's 0, 1, maybe R, it's a wolf shape of radius R, then all its principal curvatures are exactly 1 over r. This is what we would expect from a notion of a principal curvature. A ball should have principal curvatures equal to 1 over r. And there is a lemma about principal curvatures that says that if you have a hypersurface of regularity C11, and all its principal curvatures are equal, so it's kind of a totally umbilical hypersurface of class C101, totally umbilical. Then M is just a sphere, an F star sphere. So totally umbilical surfaces are spheres. This is well, more or less classical result for C2, for C11. Well, it's written in our paper, I guess maybe somewhere else as well, but you should bear this in mind. Next we introduce several functions. So we give you a definition. So delta f EA of x is just the distance function, but with respect to the F star norm. Now there is something that is called U and P. So this is the set of those points for which there exists exactly one point, which is the closest point in A to x. Now, having that, we can define something that is called the nearest point projection. And this one is defined clearly only on the U and P. Now, so the distance function, the unique set of points where you have unique nearest point, the nearest point projection function, and we also define something that is called the normal bundle, F normal bundle of A. So the normal bundle consists of those pairs A in A, U in a unit vector, or actually that should be an F star, say, so this is not a Euclidean sphere, this is a F star sphere. Okay? So A times the unit vectors, but in F star norm, such that if I go in direction U, in direction U, only a little bit, then the distance of this point to the set A is exactly S. If I go by S, it will be S. So not all points in A, of course, not all points in the boundary of A have this property, but some of them have. Okay, so this is called the F normal bundle. And we also define something that we called the F normal vector, which be just the composition of the gradient of F with the Euclidean normal vector. Now consider the following situation. Let C be the complement of the set A. P is the boundary, all essential. Okay, the essential boundary. Now we're talking about smooth sets, so just A, and take Y. It will be in U and PF, and X to be the projection onto C of Y. So the picture is like maybe something like that. This is your set A, this is your set C outside, and we take Y inside A, and we take, say, maybe somewhere here, or maybe here, I don't know. There is an X here. So this means that if you draw a ball, say, or maybe this, draw an F star ball, this is an F star ball, around Y, with Y being the center, then it touches this boundary only at one point at X. And if you have this picture in your mind, you will easily observe that the following holds. So the mean curvature of this H of X n is at most minus kappa FC1, which is at most 1 over the distance F distance C of Y. Well, we take the first eigenvalues of the first principal curvature of C, which is just outside, C is outside, and the minus, so it is the biggest principal curvature of A, actually. So the sign changes. So the mean value, this is the mean value, H is the sum of all principal curvatures. So if you divide by n, the mean value of principal curvatures is of course less than the biggest one. The mean value is less than the biggest one, and then the biggest principal curvature cannot be bigger than this one just because of the ball, because this is the principal curvature of the ball, and this ball lies inside A. So from there you get this estimate. Next we define the following objects. Z will be So Z is a set of pairs X and T. So X comes with a line segment of length at most of this length, which we should imagine that there is some X, and there you go as far as you can go in this direction. And Z, it kind of gathers all these line segments. So at each point X, at each point of the boundary, you have some line segment, maybe longer, maybe shorter, which goes inside, and so on. You have a lot of line segments like that, and Z gathers all of them. And now you have zeta, which goes from Z to Rn plus 1. It's defined by the following formula. So zeta just maps the pair xt into, well, if you have x here, you have some line segments, you go only t in this direction, and you end up somewhere inside A. And now easy computation, which I'm not going to do, shows that if you take the n-dimensional Jacobian of zeta, now the n plus 1 dimensional Jacobian of zeta. This is by definition, well, I will write it, but you don't need to really. I will take an approximate. So you take the approximate derivative of zeta, approximate with respect to this measure, hn plus 1 restricted to z, hn plus 1, well, z is of course a subset of the Rn plus 2 now, right? Because B is a subset of Rn plus 1. So you take Hn plus 1 on Rn plus 2, we restrict to Z, you take the approximate derivative with respect to this measure, and then you take the exterior power, n plus 1 power of this, and you take the length of this, or the maybe operator norm of this now operator, and this is called the Jacobian, approximate Jacobian of zeta, and you can compute it actually. The formula is as follows. This is a product of these numbers, and you get principal curvatures in here. Yeah. Now a few more facts. So facts. First fact is that the distance function is always is actually one Lipschitz with respect to some norms. Well, but from there, the Rademacher theorem says that it's differentiable almost everywhere. So the delta f is differentiable almost everywhere, and another fact, maybe more complicated, but still true. Now, this one is also complicated. I mean, the Rademacher theorem is not so easy. But anyway, so at any point where this guy is the distance function is differentiable, you actually can prove that any point where this is differentiable is in here, has a unique nearest projection. So, or to put it another way, you cannot have if you have two projections of a point, then this guy is not differentiable at the, I mean, well, yeah. So at least we have this inclusion. So if it is differentiable, if delta is differentiable at some point, then this point needs to have a unique nearest projection. So it's in the domain of the function psi. So as a consequence, we know this guy is differentiable almost everywhere, and all points where it is differentiable are in U and P, which means that U and P is actually almost everything. So but this is the same, well, Ln plus 1, sorry. Ln plus 1 of, well, we can remove U and P is just psi f c minus 1. You can put it this way, but look, the pre-image of B with respect to psi is exactly the image of zeta, right? Because it's, well, it's just equals. Well, this is true because we already noticed that this guy is less than this guy. So if you take all these line segments of this length, you fill everything in U and P. So you get this quality. Okay, now we are in the position to do the Montel-Ross argument. Let us see. From the above line, we see that this is just the measure of E is the same as the measure of the image of zeta. Now this is clearly true because any point in zeta of z has at least one pre-image, so this is clearly bigger than this one. So we integrate a function which is at least 1 on this set by the usual area formula. We can express this integral as the integral from the Jacobian. And then we have a formula for the Jacobian. We call this one. Yeah? There is a product. And I will write already using a certain geometric mean is less than arithmetic mean. There is a standard inequality between means, and instead of taking this product, I will replace it with a sum, estimating it from above by a sum, something like arithmetic mean. So let me write now. Now I can write what I was trying to write earlier. But we have to put it power n. Yeah, so using the usual inequality between means, we have this inequality. But actually, this inner integral can be computed, and we end up with the following. With the following formula. Now, this gives us the Heinz-Hartree inequality, right? Because we started with the measure of the set E. Sorry, the set is A. I'm very sorry. A and A minus, right? Because at some point I started writing everywhere E instead of A, but I always mean A. So the set that we are considering is A, right? And for some reason I switched to E, but now I changed everything to A, back to A. Good. So we started with the measure of A, and you know it's less or equal to this formula, to this integral. This is called the Heinz-Karcher inequality. But look, when is the equality? Equality, if you have equality here, it means that geometric mean is equal to the arithmetic mean. So the equality is only if this is equal and x in B, yeah? Or almost all x in B, say Hn almost all x in. And as you recall, this can only happen, this means that the surface B is totally umbilical, and this can only happen if B is actually a boundary of the full shape. Okay, and this actually, so this is the end of the proof. And this is the end of the Monti-Loro's argument, at least in case that we have smooth things. So where did we use smoothness? Well, of course, here was that we were talking about principal curvatures, right? So principal curvatures are defined only for smooth objects, even if the mean curvature can be defined for maybe singular objects. And this is the main difficulty to improve this theorem, improve this proof. To make it work for non-smooth objects, we have to use some more tools, some more advanced techniques. But the thing to remember from this proof is that it was based on the following observation. We can kind of take this whole set A and kind of express it as a sum of certain line segments, of certain intervals, like namely these guys here, right? So we express A as a sum, set theoretic sum of certain line segments, and we have to know that this all these lines, well, yeah. Now this is the main point. The main point is here that the sum of these line segments is almost everything in A. So, and then we can proceed with the Monti-Loro's argument once we know that the measure of A can be expressed as the image of this map zeta. This in general, if the boundary of A is not smooth, might not be the case, and actually we have to work to prove that it is, that this actually holds, that you can really express, that you have this equality. And for that, we need some more tools. Okay, let me state the theorem, precisely the theorem that I proved with Antonio de Rosa and Mario Santilli. So there is a theorem. Well, Antonio, me, and Mario. It was proven back in 2010, published in 2010. Okay, we have the following setup. Alpha is a number between 0 and 1. F is a uniformly convex C2 alpha norm. E is a Cacciopoli set, well, satisfying certain properties, namely, we have to assume that the topological boundary differs from the essential boundary by a set of measure 0, Hn measure 0. Of course, the topological boundary is bigger than the essential boundary. Now we also assume that the essential boundary has finite Hn measure. Okay, let us introduce this B to be essential boundary. Furthermore, we assume that the function h defined scalar product. So we define this function h, capital H, and we assume h is locally C0 alpha on C1 alpha regular part of B, if it exists, of course. And then C is just a positive number, and we assume H, the mean curvature, is now bounded by C, non-negative and bounded. and positive and bounded. Then the Heinz-Karcher inequality holds. Moreover, well, there is a finite union omega of Wolf shapes of equal radii such that, well, I should put n plus 1 here, the symmetric difference, so omega minus e plus e minus omega has measure 0. So up to a set of measure 0, it's just a finite union of Wolf shapes of equal radii. Okay, let us look at the theorem. So, yeah, we have alpha, we have a uniformly convex C2 alpha norm. We need C2 alpha. I think I'm convinced that can be this assumption can be loosened to C2 without alpha, but we proved it for C2 alpha. We are starting with a Cauchy set which has this special property. Well, this special property is needed because in the proof we are using Allard's regularity theory for codimension 1 anisotropic integrands from 1986. Where he has to assume this because of the lack of the monotonicity formula. Of course, this assumption is true whenever you have a domain with Lipschitz boundary, say. So this is not too restrictive, but still, and it seems that you have to assume something like that, at least as long as we don't have more powerful regularity theory for anisotropic integrands and manifolds which has mean curvature in LP with respect to some anisotropic integrand. So this one comes from Allard's regularity theory that we have to use, and then here this is CO0 alpha. Well, we are also using certain classical regularity theory for PDEs of fully nonlinear divergence form PDEs, and we have to at some point know that H has some Helder regularity to be able to use some kind of Schauder type estimates to bootstrap it to C1 alpha or C2 alpha. Okay. Yeah, so these are the assumptions, and then we prove the Heinz-Karcher inequality, and then from the proof, actually, because it's the Montiel-Ross argument, as before, we deduce that equality holds only if we have Wolf shapes, finite union of Wolf shapes. As I said, to do the Montiel-Ross argument, we actually need to know that this function zeta covers almost everything, right? We need to know this property. So there are two pillars on which our proof stands. One is the so-called Lucin N condition. So let me define what does it say, definition. So A is said to satisfy the Lucin N condition in some open set U if the following holds, the following implication holds. Say I have a set S, which is a subset of A cap U, which is a null set with respect to the n-dimensional Hausdorff measure. Then this should imply that the normal bundle of A over the set S also has Hausdorff measure 0, right? So this basically means that if you have you have this A here, and you have this normal bundle is like attaching to each point. Kind of the normal bundle is kind of a distance set, something like that. Well, it's an abstraction of the distance set, and if you have like here some set which is of measure 0, so this S consists of some strange set which has measure 0, and we look only upstairs also on what is above this set of measure 0. So this set above should also have measure 0. This is basically what the Lucin N condition tells us. Great. And the main point of the proof of our what is novel in our proof is that we note that we prove actually that if you have a varifold with bounded mean curvature, anisotropic mean curvature, and satisfying this additional property, codimensional varifold, associated to the boundary of E, to the essential boundary of E actually, and and you know that there is this special property that, if you take the closure of the essential boundary, which is basically the topological boundary, the closure of the essential boundary differs from the essential boundary by a set of measure zero. This is always what we need to know. So if you have a varifold, if this varifold has bounded mean curvature, which is this property, and has this property, then we can prove that it has the normal bundle, or that the support of V has the Lucene N condition. So there is a lemma. B satisfies the Lucene N condition. This is proven using certain result of Guido De Filippis, Antonio De Rosa, and Jonas Hirsch from 2019, where they prove where they study certain sets such called the blow-up sets. Blow-up sets for bounded mean curvature submanifolds. So if you have a sequence of varifolds which have uniformly bounded mean curvature, and you look at the blow-up set, which is a set where the set of points whose neighborhoods kind of tend to have bigger and bigger measure in the limit of this sequence, because we're talking about sequences of varifolds. Then this blow-up set is an NH set, and NH sets have Lucene N condition property, and B satisfies all of this. So using these tools, we are able to prove that B satisfies the Lucene N condition. And the second thing is the regularity theory. So yeah, so for that we of course need to use this assumption that H is C0 alpha locally. So first for this lemma we use Allard's 1986 regularity paper to get C1 alpha. So we have that B is almost everywhere C1 alpha regular, and then we use classical PDE Schauder estimates, kind of for fully nonlinear divergence form operators. To actually bootstrap C1 alpha to C2 alpha, and we need it because then we know that B can be covered, right? I mean, there is some zero set, null set. We can, if after removing a null set from B, Hn null set of B, the rest is a C2 alpha manifold. Why do we need it? We need it because once we know that some point is a C2 alpha point, at this point we can express the F mean curvature by sum of the principal F curvatures, or F principal curvatures. And for that single point, we can do some we can use this computation for the Jacobian of zeta here. I mean, this computation of the Jacobian uses the principal curvatures, and if you are smooth, you can do that. So in this case, at smooth points, at C2 points, C2 alpha, we can use the same formula for zeta, for the Jacobian of zeta. But still, and for that, well, using the Lucene N condition, we can derive conclusion that actually the image of zeta is exactly the whole, almost all of A or E or whatever it's called. In this theorem, it's called E. Yeah. So using Lucene N condition, we derive that zeta, the image of zeta, covers almost all of E, and then on all C2 alpha parts of B, we can use the same argument as before to prove that they are totally umbilical. So so B, now we know that B consists of, I mean, maybe countably many pieces of Wolf shapes, of boundaries of Wolf shapes, right? But this is actually not the end. It's not enough because we don't know how these parts, maybe countably many, are composed in space to form the whole set B. So we still need we once again need to use the Lucene N condition, and we need some more arguments. So what we do, we derive some characterization of positive Rich sets, positive F Rich sets, using some kind of Steiner formula, and using this, we proved that our set B has the Steiner formula, so satisfies the Steiner formula. From there, we know it has positive F Rich. And then we can work with level sets of the distance function. So we work with the set this is a distance level set of the distance function, and this set a priori, because delta is one Lipschitz, is a Lipschitz manifold. SFCR is a Lipschitz manifold, and we can actually we can compute principal curvatures of this guy for all points which come from C2 alpha regular points, which are Hn almost all of B, right? So we can compute the principal curvatures in terms of the principal curvatures of B at the point of the corresponding point, and see that SFCR is a totally umbilical. Well, at least at points, at C2 alpha points, which is almost all of SFCR. And then a boundary of a Vulchik. Great. And this is basically the end. Well, going with R to 0 and passing to the limit, we can actually show that B has to be some, countable sum of boundaries of Wolf shapes. Okay, and this is the end. So the main point is I think the main ingredient, main novelty is to use the Lucinen condition, which is this Lucinen condition is an invention of Mario Santilli, and it works. Okay, thank you very much for your attention.